Hello everyone, my name is Manuel Fedou. I'm an application engineer for electrification at Speedgoat. In this webinar, we will present how to accelerate development of power systems with real-time testing, from renewable energy integration to the development of onboard systems. We will explore following concepts. Real-time testing can be used to design and test control strategies and systems required for power generation, transmission, distribution, and for onboard power systems. Real-time testing allows to expedite control systems innovation for more diverse energy sources, integration of renewable technologies, smarter grids, and hybrid and electric power systems. You can easily transition from Simulink-based desktop simulation to real-time testing with your hardware. We will cover following topics. First, we will go through power systems challenges and how real-time testing can help. Then, we will go through power generators development and their integration in the grid. We will explore power transmission and distribution, and we will finish with onboard power systems. But first, let's see which challenges are common to all those power systems and why we need real-time testing. First, real-time testing enables you to accelerate time to market. You can adopt a control prototyping solution, enabling rapid innovation independently from the production hardware configuration. With this, test and prove new ideas, integrate new components as you change requirements. It takes you one click to build a real-time application and run on target. Second, with real-time testing, you can detect design flaws at the earliest possible stage. Analyze and compare desktop and real-time simulations to detect design flaws in your models and algorithms. Prove concepts, inject faults, and test environmental conditions. Take advantage of signal monitoring, data logging, and parameter tuning capabilities. Third, you can perform automated and extensive testing. Simulate physical plants to enable continuous test and integration when the actual hardware is not available. Perform and automate tests in a safe environment without risks of damaging equipment or injuring operators. Let's see how to apply these benefits to our topic of today, power systems. But what do we mean by power systems? Power systems analysis can be seen across different domains. First, power generation, developing new power generators, testing them, and testing their integration in the electric grid. Then, testing power transmission, power distribution, and microgrids. Third, onboard power systems, which are in many ways similar to microgrids. We will cover electric ships, aircraft onboard power systems, and electric vehicles. Let's look at typical market drivers for real-time testing for power generators. Power generation technology requires ever-increasing power levels, power efficiency, and greater fault tolerance to help build a more resilient power grid. Solar or wind farms require complex control strategies and certification. Real-time testing allows to rapidly design and test control strategies and to test proper functioning and assess compliance of equipment prior to development. In the case of electric grid, diverse power generation technologies increase integration testing requirements for software, hardware, safety and security. Diverse power sources and increasing electrification of onboard power systems require smarter grids, and increasing fluctuation in power supply to grid and changing power needs require additional power storage, management, and forecasting technologies. Grid real-time simulation provides an ideal tool for integration testing and to simulate and test grid resilience. Onboard systems in automotive, aerospace, or marine domains present similar challenges as smart grids. Different types of generators need to be integrated, power needs to be managed, and electric loads need to be controlled. Ongoing electrification, climate change, and changing end-user requirements require a very high innovation pace to remain competitive. while at the same time maintaining quality levels. With real-time testing, you can rapidly innovate, test, and prove new control ideas, thoroughly test and automate testing of control systems with hardware-in-the-loop simulation of digital twins. This timeline represents a model-based design path without iterations, with the objective of showing you how controls development and testing benefit from real-time testing. With model-based design and real-time testing, you can go from early designs through all the iterations and test cases via flexible prototypes. You can use real-time simulation for rapid controller prototyping or for hardware-in-the-loop testing, but also other use cases such as power hardware-in-the-loop or virtual commissioning. Regardless if you are trying to build an HL simulator to test your embedded controller or rapidly prototype controls, vision, or signal processing algorithms, you can adapt your desktop model for real-time simulation and testing with just a few steps. Rapid control prototyping allows you to swiftly test and iterate your control design early in the development cycle. It allows you to speed up software development, expose design flows earlier, and shorten time to market of your embedded controller. But you need powerful and flexible hardware to be able to directly run your simulating designs and connect with your physical plant. Embedded controllers typically are not flexible enough because you cannot easily add or modify I/O interfaces to deploy new designs. Also, you cannot easily monitor, log, or fine-tune data during real-time execution. The second key use case is hardware-in-the-loop simulation, or HIL for short. HIL simulators allow you to test and validate your embedded controller versus a simulated plant running in real time. This is a great way for you to reduce cost and safely test your embedded controller in a reproducible and automated way in scenarios that would otherwise be hard to mimic in real life. Another HIL setup is Power HIL. Typical setup for Power HIL could look like that. It is comprised of a power amplifier in between a device and a test, like the three-phase power part of a solar plant or an energy magazine of an electric ship, and a HIL simulator. Amplifier and Speedgoat real-time target machines are connected through a high bandwidth fiber optic connection. With Power HIL, you can test your electrical component like integrated on the power grid or in an onboard power system. Now let's map these technologies with some of the challenges we mentioned for power systems. To accelerate development of complex power systems, leverage rapid control prototyping. Then, to thoroughly test your design against expensive or non-available equipment, to perform integration testing of components with avoiding downtimes, to manage interoperability between different levels of power systems control, to ensure compliance with certification requirements, to execute operator training and predictive maintenance, you can use hardware-in-the-loop and power hardware-in-the-loop. Let's recap real-time simulation and testing workflow with Speedgoat. It is made for Simulink with a vast range of I/O protocols, built for speed, scalable and configurable, and perfectly integrated in the MATLAB toolchain. Perhaps you would like to integrate in your power systems motor controls with motor control block set, or to model power electronics and power systems, then consider Simscape Electrical. You can use Simulink Test to automate testing in real time. Let's now recap the Speedgoat hardware portfolio. Speedgoat provides real-time target machines for office, lab and field use with more than 200 commercial off-the-shelf I/O modules. Machines are configured to meet your sample rate, I/O and environmental requirements, and we support latest MATLAB release. Let's check the I/O connectivity and protocol support. I'll pause for a few seconds. No matter whether you are prototyping control strategies or testing controllers against your digital twins, connectivity shouldn't be a hurdle for you. We are supporting key protocols for all industries, including, for example, DNP3 and Modbus. We have covered power systems challenges and introduced real-time testing with Speedgoat. Let's now focus on power generation. Here are some typical use cases for real-time testing of power generators. For research and prototyping, you need to accelerate lab experiments and to test and develop new concepts without embedded devices. For that, leverage rapid control prototyping. Then, to test controllers of power generators, use digital twin of multi-domain power generation systems and plug-and-play I/Os to interface with sensors or emulate them. You can do that with HIL for multi-domain power generators. To test integration of power generators in the grid and test compliance with grid regulations, use HIL for power systems analysis and Power HIL. We are going to go through these different use cases with the example of wind turbine development. And we start with development of prototypes when engineers are developing and testing new concepts. The success story of the British company Wind Technologies is a good example of how you can use rapid control prototyping for power generation. They developed controls for brushless doubly fed induction generators, offering significant cost reductions and reliability improvements when compared with conventional doubly fed induction generators. To quickly prototype their design, they used a Speedgoat machine to deploy their controls in real time and control the generator. The ability to easily and effectively transfer code from Simulink to the real-time target machine has resulted in a significant time saving over the course of the project. Later in the development process, you will need to test a controller, which could be a PLC in the case of a wind turbine. You can take advantage of HIL for testing your power generator controller. HIL can replace prototypes or production hardware with a real-time system. It enables to automate testing more easily with tools such as Simulink Test. It is safer to test with real-time simulations than with most power generators hardware, which can break down. We're dealing with very expensive and dangerous hardware here. It enables to start many design and test tasks earlier because you can test controllers even if the hardware is not available. But for that, you will need a real-time simulator of a power generator, here the wind turbine. And for that, you can use Simulink and physical modeling tools to create a multi-domain digital twin of the generation systems. In our case, let's look at the multi-domain model of a wind turbine connected to the electric grid. Our model is including electric generator, 3D mechanics, controls, supervisory logic, and a grid model. This enables us to test a wind turbine controller based on a state machine. Let's directly simulate that model on a real-time performance machine. I open the model in Simulink, and in one click I can go from desktop to real-time testing. The model is compiled and loaded on the Speedgoat target. External simulation starts and we can inspect the results. Let's inspect the state machine and observe the state start animation in real time. We are simulating the startup of a wind turbine. First, the wind turbine is parked, then it starts accelerating, and when it reaches sufficient speed, we can generate power and connect to the grid. Let's open a scope and look at electrical power as soon as generation is activated. Let me introduce you following user story about wind farm development from the company Hydro-Québec. Hydro-Québec engineers use Simulink and Simscape Electrical to model and simulate individual wind turbines and entire wind farms. They use Simulink Coder to generate code for real-time simulations, as in our example. Accurate modeling is essential not only for planning investments, but also to detect situations that can cause an outage. With MathWorks tools, they can simulate power electronics, mechanics, and control systems in one environment, and their models respond like the turbines in the field. So we focused on the power generator itself with multi-domain physical simulation. Now, let's consider the wind or solar farm from the perspective of how it interacts with the power grid. Why is it so important to analyze how this device is going to affect the grid? Well, we are dealing with interconnected systems. Distributed resources are tied into interconnected grid. Then, we are dealing with non-dispatchable generation. We have variable power production depending on whether variable resources such as wind and solar. Simulating this is going to involve a lot of historical data. And third, we have controls such as reactive power control and protection coupled due to interconnection. So we need to test the interoperability. Because the system is so interconnected, this interconnection needs to be regulated. We here focus on renewable generators, but for traditional, it is the same kind of challenges. The idea is to define how the device should ask in specific cases, such as low voltage, so that we avoid cascaded scenarios that could result in a blackout, for example when a bunch of devices drop at the same time. Grid codes add a boundary to such scenarios. For example, in cases where the grid voltage drops, you have standards defining if the device must stay connected to the grid or when it must trip. Similar codes also apply in the frequency domain. Let's look at grid codes commonly used in the US. For example, we consider IEEE 1547 grid code, typically used for distributed energy systems. We have a voltage write-through and a frequency write-through code. For the voltage write-through, the grid code defines that for a short voltage drop, the device must write through. For longer or stronger voltage drop, it may write through, but for an even longer or stronger voltage drop, the device must trip. Let's build a model to simulate and test our system. We are considering the system at a higher level here, focusing on the simulation of the devices together with the grid. We're using Simscape Electrical specialized technologies to build the model. This is the model of the interface of the solar and wind power generators to the grid that we are going to simulate to validate grid code compliance. In this model, we are testing an algorithm for grid code check. This algorithm uses some grid measurements to decide if the device should trip or not. Typically, you would implement the protection and control algorithm on a production system or on a real-time automation controller. You would have to test against a prototype or the physical system. We want to use a Speedgoat system to simulate the equipment in real time in order to test the controller with Hill. Let's start the simulation from Simulink directly on the target. The simulation starts and we can inspect the results in Simulink Data Inspector. On the top, we are plotting grid voltages, and on the bottom, you have generated active and reactive power. We are simulating the grid voltage drop. First, the power generator will stay connected, but after some time, according to the grid code, the device trips from the network as defined by the must trip condition of the grid code. Then, for performing Hill testing, you would deploy the grid code check algorithm to a protection relay, add Speedgoat I/O blocks to your Simulink model. Here you could use, for example, I/O 758 for Ethernet IP communication, and then perform Hill and test your controller. We have covered power generators. Now we are going to explore real-time testing of power transmission and distribution systems. Typical challenges for controls of power transmission and distribution are schedule and dispatch of units under supply and demand uncertainty, reliable and economical operation of microgrids with high penetration levels of intermittent generation, bidirectional power flows at the distribution level, development of new voltage and frequency control techniques, interoperability of controls at different levels. For that, you can use Hill for power systems analysis and Power Hill to test integration of devices in the power grid. Grids typically involve a controller and some protection devices. Real-time testing enables to test such controllers safely. For that, we are going to emulate the grid in electromagnetic transient EMT or phasor-based simulation, perform distributed simulation on multiple cores and targets. This enables to test grid controllers or control protection devices. To connect the controller to the simulator, We use I/O protocols such as EtherCAT, Modbus, Profinet, or IEC 61850. We can also test power system components inside a virtual grid with PowerHill. There are different levels of grid controls with control transients ranging from microseconds, milliseconds to seconds and to hours. We can cover these different levels with our I/O modules and simulation technologies. Depending on the application, you can perform phasor simulation or EMT. Phasor-based simulation enables us to test on a higher level grid control and management. Typically, simulation sample rates are around 1 millisecond or more. EMT simulations, on the other side, are useful for production studies and require smaller time steps. You can also combine both simulations depending which part of the network you need to be testing. Hill and PowerHill are great tools to test flexible AC transmissions. Facts. You can test power flow control, reactive power control, voltage control, power quality improvement, and harmonic mitigation. You can leverage examples for static synchronous compensator, STATCOM, static via air compensator, unified power flow controller with phasor or detailed models that you can run on real-time equipment. In the case of PowerHill, you can emulate transmission to test fax devices, for example. The exact same applies for high voltage direct current transmission, HVDC. Let's look at HVDC model with all levels of controls. We have rectifier and inverter primary and secondary controls and a master control. We loop back the master control with DMP3. The output of the master control is sent via DNP3 master. On the other end, we have modeled a DNP3 outstation capturing data coming from the DNP3 master. We ran this loopback test in real time. Let's run it. And with this, we can validate the DNP3 communication. We can inspect simulation results and see that the operating points are sent successfully by the master control via DNP3, that the primary and secondary controls regulate the grid voltages and currents accordingly. Here we focus on one key protocol for power systems control, DNP3. Distributed Network Protocol, DNP3, is a TCP/IP-based communication protocol used in the power generator and distribution industry. It allows communication between SCADA systems and remote terminal units, RTUs, or intelligent electronic devices, IEDs. It ensures interoperability in the electric grid and empowers you to design and test smart grid applications and protection features in power stations, which is exactly what we tested here. We support DNP3 master and slave. There is a nice success story for HVDC transmissions. Alstom Grid used model-based design with MATLAB and Simulink to model, simulate, verify, and generate code for the HVDC control system. They developed a conceptual design with Simulink and StateFlow. Using Simulink and Speedgoat Electrical, they built a plant model that included an AC grid connection, transformers, and loads. To verify the control design and plant model functionality, they ran closed-loop simulations in Simulink. Next, they refined the control algorithms in preparation for deployment to a real-time target. Okay, now let's move to real-time simulation of distribution networks. We can consider an example of the IEEE European low-voltage test feeders having the following attributes: 906 three-phase buses, 55 loads. We rely here on time series simulation results over a one-day period and static power flow calculation results. This network can be simulated using a phasor approach, the goal being here to test a high-level grid controller device. This network can be first simulated on desktop. Speedgoat Electrical compares very favorably in benchmark testing. The layout can be represented using the MATLAB graph function. Segmentation is calculated using tools from graph theory. Then we can model the system in Simulink. Here, what we're going to show is explicit partitioning. We use model referencing to split the network in different regions that will run on separate cores. Segmentation and multi-core execution allows to scale up simulation. Segmenting the model introduces algebraic loops which must be broken. This means that there will be some small transients introduced into a segmented system response compared to the full model. We can, however, mitigate this effect. Next, we use MATLAB scripts to automatically build the network. We are not going to build these huge models per hand. IEEE network data are passed by MATLAB scripts that generate the Simulink model. Here you can see a visual demonstration of how such a network can be built. For explicit partitioning, we define how concurrent execution will be set up on the target by the different tasks. Then we build the real-time application. We generate C code from the Simulink and Cipscape electrical network and build the model to run on the real-time target. Because of the size of the network, this requires several minutes using distributed computing for generating code from the different reference models. At the end, an application file is generated which can be used to deploy on a target. Now we can deploy the real-time application to the target connected to the computer from the MATLAB command line. We connect to the target, load the application, and start the real-time simulation from MATLAB. Let's open the Simulink Data Inspector, where simulation results are streamed. We can observe the result of the phasor simulation and inspect different voltages and currents. In our case, the simulation is set up to have a change in the load parameters every 0.6 seconds. We can measure task execution and validate the multi-core execution of the model. We still use the same application and target objects. We first enable profiling, then run simulation on target for a couple of seconds, and then we can retrieve profiling data from the target. Let's open profiling results. We can check execution time and how tasks were distributed on the different cores. As a result, we see that the task execution time is very well distributed on the 4 targets. Distributed simulation allows us to reach a sample time of 4 milliseconds, which could not be reached without multi-core simulation. For simulating bigger networks, we can distribute the simulation on multiple targets. To summarize, you can scale up grid simulations with multi-core and multi-target execution and use low latency interfaces such as Aurora or shared memory. When choosing a solution for multi-target timing and synchronization, you need to consider the distance between the individual system components, the requirements on timing accuracy, and what types of interfaces are available or preferred. Speedgoat offers support for common timing protocols like PTP or iRig for local devices and connection to third-party devices. For long-distance synchronization, GNSS receiver can be used to receive globally available, highly accurate clock signals from satellites. Many Speedgoat I/O modules are equipped with clock and trigger pins for synchronization, and additionally, specialized modules are available to add ultra-low latency communication. Now we can look at a specific use case where power generation and distribution are mixed up, microgrids. In microgrids, power generation devices are integrated in the power network. In this microgrid, we have solar panel power generation producing variable power depending on weather conditions. We have an energy storage system and feeders, and the microgrid is connected to the distribution grid. Here we will test a microgrid controller supporting operations such as islanding or peak shaving. We can run that model in real time. We are plotting in blue the energy flowing from the utility grid to the microgrid. It is negative because we are producing electrical power and delivering power to the grid. In orange, you can see power going to the energy storage system. As we are running this model in external mode, we can change set points on the fly. We can also island the microgrid from the utility grid. And you can see that the blue curve goes to 0. We can also test reconnecting the microgrid to the utility grid. And we can also introduce changes in the weather condition from clear to cloudy, which affects, of course, the generated power. Let's inspect grid currents and voltages, which are affected by the islanding operation. Let's look at the power delivered by the battery. And let's inspect electrical power generated by the solar generator, dropping when we introduced the changes in weather conditions. Here, I would like to point out an I/O module supporting many different protocols that are very popular in microgrid controls, the multi-node simulator-32, which can be used together with any of the Ethernet-based I/O modules from the IO75X generation. It is capable to physically simulate a high number of slave and master nodes. It can be used for many different applications, such as industrial installations, production plants, ships, wind farms, solar parks in the power grid. This module can be used to interface Simulink with multiple programmable logic controllers, power analyzers, power converters, inverters, grid protection relays, and many other industrial equipment. There is a nice success story about DC microgrid development from the Mondragon University. Using hill testing enabled them to accelerate the control development of DC power converters and helped assess DC microgrid stability under different operation conditions. They praised Speedgoat Hill solution as a versatile platform to include different levels of model fidelity to assess the grid stability on different operating conditions. We can conclude this chapter on transmission distribution. Let's move to onboard power systems. We will cover onboard power systems for marine, aerospace, and automotive applications. Onboard power systems require detailed system-level analysis. Planning of power generation is critical because some devices may require a large quantity of electrical power over a specific period. For that, you can test controllers with hardware-in-the-loop testing. Integration of power components needs to be de-risked, and we need to make sure that equipment can handle faults. For that, you can add power hill. Operators need to be trained, and maintenance of those equipments need to be supported. And for that, you can use simulators as virtual commissioning platforms. All-electric ships and hybrid solutions typically include an integrated power system, connecting power sources, loads, energy storage systems, and electric propulsion modules in a zonal electrical distribution system. The vast complexity of such marine power systems require a thorough evaluation and validation phase and performing integration tests and simulations to guarantee the interaction of many electrical parts before building the actual ship. We are going to explore an example model of an electric ship. In this demo, we present a hardware-in-the-loop testing of the microgrid architecture of a fully electric ship. We will be implementing an industry reference architecture from the Electric Ship Research and Development Consortium. The two-zone onboard grid will be deployed to a Speedgoat target computer at 20 kHz. Such model covers not only electrical components, but also gas diesel engines, power electronics, batteries, and electrical motors. Actually, the microcontroller under test will be controlling a propulsion motor using field-oriented control. For this model, we introduce AC generation and control. Each generator consists of a silent pole synchronous machine, a gas turbine, and an AC1 exciter. We have an ideal AC-DC rectifier, and we have modeled the motors as permanent magnet synchronous motor machines with field-oriented control so that we could evaluate a broader range of operational responses. In particular, we wanted to simulate a stylized full-ahead crash stop. What we mean in full-ahead crash stop is we like to evaluate the performance of the drive during quadrant 2 regeneration. For the purposes of this example, we created a stylized piecewise linear torque speed curve where you can see an incursion into quadrant 2. The time period of the maneuver is condensed, so we could see the response in reasonable time. In the power plot, we see negative power between 18 and 20 seconds, so we confirm that the propulsion motor module response is functionally correct for this scenario. We can start the model on the real-time machine and inspect generator and motor power outputs. Then we can start setting up Speedgoat FPGA driver blocks to communicate between the TI board and Speedgoat target computer. We use quadrature encoder drive blocks to connect to the target, and we use PWM capture blocks to receive PWM signals from the microcontroller. This means that we are simulating the onboard systems together with power electronics component to add more fidelity to the modeling and to be able to test interoperability between different levels of controls. As the hardware design progresses, we can add detail to the plant model resolution to make a wall hill testing closer to reality. Here's the simulation results that meet our expectation. The speed control is behaving as expected, and we see double humps on PWM signals for inverter. Like electric ships, onboard power systems for more electric aircraft are similar to microgrids. We have power generators, electric motors, energy storage, and electrical distribution. Let's consider an example model of a more electric aircraft. The model has the following components: two Brayton cycle gas turbines, gas, thermal, and mechanical domains, two permanent magnet synchronous generators with feeder-oriented control, electrical and thermal domains, two PMSMs with FOC control and ideal speed reference, electrical and mechanical domains, two DC-DC converters, and four PMSM actuators with average value power converters and FOC control. I'll open the model so we can have a look in more details. The Brayton cycle gas turbine are modeled using gas and thermal domains. As you can see, we connect the generator to the main shaft using a constant speed drive. On the electrical system, we drive the permanent magnet synchronous machines with feeder-oriented control. We feed the modulation wave to an average value converter so that we can see the EMT responses without harmonics. And we also have the PMSM drives for some actuators, such as ailerons. Let's now simulate the model on a real-time platform. We load the model and start simulation. We can inspect results in real time in Simulink Data Inspector. The output power curves for diverse motors and generators are plotted, and we will look at specific responses more in detail. We see generator power ramps to around 250 kilowatts. Negative means generated power in this case. In this scenario, we are ramping the power consumed by the electric turbines and have instructed the energy management system to use battery power when the generator reach 250 kilowatts. So we are seeing expected response here. Note that the ripples that you are seeing is a consequence of the actuators cycling from positive to negative angle. Here we see the angle of the left aileron cycling from positive to negative. This is a duty cycle driving the left aileron motor. If we zoom in, we can see a double hump, which is what we expect to see when using space vector modulation. Here we see the thermal response of phase A stator winding in both generator 1 and generator 2. Only generator 1 has active cooling, so we can see the difference in the response and confirm that the active cooling circuit is functioning as expected. In this case, the active cooling circuit is configured to regulate temperature to 60 degrees Celsius. For the purpose of this demo, we have parameterized the system to show a thermal response in only a few seconds of simulation time. The task profiler lets us see task execution time at different rates. The Base rate is electrical sample time, which is 50 microseconds. Subrate 1 is a sample time associated with the gas turbine, and subrate 2 is a sample time associated with the generator thermal system. There are two things to note here. First, the model sections associated with the different sample times have been distributed to different cores. This is known as implicit concurrent execution. We have explored explicit partitioning in our distribution grid demo. Second, the thermal system takes around 2 base rates to execute, and the gas turbines takes around 3 base rates to execute. This tells us that we would be unable to simulate the full system in real time if we did not split the sample times across the different model sections. You can simulate electric vehicle onboard power systems in a similar way and combine with powertrain for full vehicle simulation. For instance, using powertrain and vehicle dynamics block set, you can rapidly assess electrified powertrain capabilities. These tools provide you with a great starting point to build electrical or hybrid vehicle models with well-documented reference applications. One very important aspect for all onboard power systems is energy storage systems, for instance battery packs. You can add battery pack models to simulate battery cells and generate fault scenarios. You can perform diagnostics on cell level, measure voltage between cell terminals. In this example, the measured cell voltage values are fed into a driver block for the IO 991 module, which converts these numerical values into electrically isolated voltages, each relating to individual battery cells. Let us conclude with a success story on battery management systems. Leclanché Energy Storage Solutions is developing the next generation of lithium-ion battery packs for autonomous vehicles. Being unable to properly test and verify new BMS algorithms before operation with real battery packs, Leclanché starting using Speedgoat battery cell emulators for hardware-in-the-loop testing of their BMS algorithms. Such tests required also using fault insertion and a communication protocol like CAN. They were able to thoroughly validate their BMS and state estimation algorithms, thus reducing test time by around 50%, increasing coverage and finding bugs at an early stage. Now we reach the end of this presentation. So I conclude with these 3 key points. Massrock tools, together with Speedgoat, provide a unified control design and testing platform for power generation, power grid, and onboard power systems. You can easily transition from Simulink-based simulation to real-time testing with your hardware, and you can test embedded controllers and electrical power components faster. Many thanks for your attention.
You want to learn more about real-time controls testing? Then find additional content linked here.